Hello students, welcome to the second session of our first module of the subject Mechanics of Solids. So students, in the previous session, part 1, we have studied the basics of mechanics of solids. How is it different from the subject you have learned in the previous semester for engineering mechanics? We have discussed the difference between deformable body and a rigid body, and how is deformable body mechanics different from rigid body mechanics. Okay, and we have also learned the concept called internal force and we have studied it using the method of sections. I will explain it once more for those who have not understood that much. Okay, suppose I have a body, a rectangular body having a rectangular cross section. Okay, let me apply some force initially, some force of some 1 Newton here and equivalent opposite. So this force is a tensile force because it is axial, and also stretching it towards outwards, right? So what will happen if I am applying 1 Newton of force? uh, it will extend a little bit, right? So initially if it was some 10 centimeter length, suppose I have applied 1 Newton of force. Naturally the length of the body get increase, right? Stretching takes place, right? Why? Because I have applied a force of some 1 Newton. I am taking just an example. This may not be the correct increase in length. I am just taking an example. Okay, so it have increased by some 1 centimeter. Right. Again, so what will happen if you take a section here? I will show. So I had 1 Newton of force now, not increase from 1 Newton. Still 1 Newton is there, present there. It is being applied. Okay, since I am sorry, I'm taking a section. So it is being cut into two parts. Okay, so naturally some in 1 Newton is here, 1 Newton is here. Naturally here some internal forces will be developed. So at present 1 Newton of force is being acted, some external force is being acted on that body. A body whose length was 10 centimeter has increased to 11 centimeter. And what will happen internally? Internally some internal force will be generated. What will this internal force do? This internal forces try to resist the effects of this applied force, right? These applied force. So these forces try to counter the effects of the applied force. So what will happen? Since this developed force is also 1 Newton, here also 1 Newton, the net effect of these forces will be 0, right? So an equilibrium will be maintained. So now the body will be remained at a length of 11 centimeters. Some equilibrium will be maintained. Now again this 11 centimeter body was there. Now the length is 11 centimeter. And I have increased the force, applied force to some 2 Newton. Okay, what will happen? Again stretching will take place, right? Again stretching will take place. Elongation is the correct word. Maybe some 12 centimeter, 12 centimeter, right? 12 centimeter. Force was 2 Newton only. 2 Newton only. Now, what will happen to the internal force? Internal force. Naturally, internal resisting force also will increase to match up this external applied force, right? It will also get increased to some 2 Newton so that equilibrium can be maintained. So, no longer the stretching takes place. No more stretching will take place, right? Stretching or elongation more than 12 centimeter won't take place. That's how elongation, that's how internal force works, right? I'm taking a section here, xx. Okay, now for this section, some force of here 2 Newton. This will also be 2 Newton. This force also gets increased. This is also 2 Newton. This also 2 Newton, right? So why is this internal force is being generated? This internal force is being generated as a part of the property of that material due to the cohesion. Have you heard of the word called cohesion? Cohesion is the property of some material particles to stick together and uh, counter the effect of applied force without being elongated, preventing, resisting it from being elongated. That's the word cohesion. All the similar homogeneous particles being stick together so that no elongation, no nothing, no changes being have no changes will be possible for that particular body. So that's due to that cohesion, this internal force is being generated. So students, you have to remember the fact that whenever so now this is some 12 centimeter long, 12 centimeter long. So here 2 centi 2 Newton of force is now applied on that is present on that body. Suppose I am removing these tensile force. So what will happen? I am no more applying this force on that particular body. What will happen to that body? Simple, right? Because since in every section there is anywhere in that body, internal forces are being present, right? Internal resisting forces are there. uh, if I have removed this applied force, what will this suppose I'm taking this section, this particular section. Okay, here some 2 Newton internal force is there. When I have removed this 2 Newton external force, so here 0, force is equal to 0. Here also force equal to 0. If I remove this force, what will this internal force do? This internal force will bring back bring back those elongated material back to its initial place, right? So friends, students, if you just think about a rubber band, you have elongated that rubber band using some force. When you remove that applied external force, the elongated rubber band will move back or will regain its original size or shape, right? It will regain when the applied force is removed. It will regain its original size, right, or shape. So why is that happening? Because of the internal forces present on that body, which was generated due to applied force. Applied force generated internal force. When the applied force is removed from that body, this internal force will move or will help the body to regain its original size or shape. Okay, you getting the point? You getting the point, right? So that internal force, that internal force will give the idea of the strength of that material. Will give you the idea of strength of that material. The extent up to which. Okay, I will show one more example. I will. So it. Our body was some 12 centimeter when 2 Newton of force was applied, right? If I again increase some to some 10 Newton, it may become some 20 centimeter or what? Okay. For example, 20 centimeter, some 10 Newton force made that body to a length of 20 centimeter. 20 centimeter. If I have increased the force again to a particular value, at some particular value of force, the internal force has reached a limit. If no matter how much amount of external force you have increased, internal force won't increase up to that level, because the limit has reached the limit. Suppose I have increased to 12 Newton. 12 Newton. Okay. Now, the if I have taken a section XX, the internal force will be 10 Newton only. 10 Newton only. Because for this particular material, it's a limit. The limit of internal force is just 10 Newton, above which it cannot increase its internal force. So, what do you mean by that? If you increase the applied force more than the limit of that more than the limit up to which the internal force can be generated in that particular body, it means the body will break, right? The body will fail, not break. It's called some cracks will be formed because some maximum has reached the maximum of that body, the maximum external force that body can tolerate or withstand has reached. That was 10 Newton. Some value above 10 Newton means it can no longer the body can withstand that force. It will break somewhere, some cracks or some failure will occur in some arbitrary position of that body. So you will learn about all these things in the coming modules or chapters. So have you understood? So for example, if you have a some rubber band or rubber band, example rubber band, just you have a rubber band. Some this uh, let this be a rubber band. So if you stretch this rubber band uh, up to some level and you remove that force, means it will regain. I'm applying some force, it is elongated, and if you remove that force, means it will regain the original size. But if you stretch the rubber band or elongate the rubber band to some higher value of force, sometimes the rubber band may get torn, right? It will be torn. It will be broken, right? It will be made into two pieces, right? So why is that happening? Because its limiting value, the maximum value of force that it can withstand has reached. That is why it's so when when maximum force or load that it can withstand is reach the material, the material will fail, material will fail. So this is the point you have to uh, remember, right? Now another important point, the maximum load that uh, that a substance, a body can withstand depends on what? Depends on what? Can you guess? It depends on the material, material of that body, material by which that body is made of, right? Material of that body. Because if I in the example I have shown a rectangular road, or a body with a rectangular cross section. If it was made by steel, maybe made of aluminum, made of iron, made of copper, uh, all the different material will have different value of maximum load that it can bear, right? Why it's so? Because the strength of material, the strength of that body depends upon that material by which it is made of. That's very important, because each material has got different strength, different strength. Okay, so the internal force that it can the internal force that is developed uh, gives the measure of strength of that material, strength of that material. Are you getting the point? So strength of that material, the internal force, the extent to which internal force can be developed in that particular body, measures the strength of that particular material. Okay, suppose that body, when I have applied some 5 newton of force on that body, okay, the internal force may generate up to 5 newton, and above which the internal force may not increase matching with the external force. So that and another body can withstand up to 10 newton of force, means the second body has got a strength of a higher strength, a more amount of strength for the second body compared to the first body. That's the meaning, right? That's the meaning. Are you getting the point? Okay. Now I will move to the concept called stress. Very important. Stress. What do you mean by stress? So I have a body. I have a rectangular body. Let me apply a tensile force of value of F. Okay. Now the cross sectional area of this body, let the cross sectional area of cross section equal to A. What is this area? This area is A. Then what will happen when a tensile force is acting on that body? Suppose I am taking this particular section, I am cutting at that section XX. Okay, what will happen? Some internal force will be generated, right? Some internal force. this is F, this is F. Here also some internal force will be developed, right? Here also some internal force will be developed. Okay, so this force is nothing but internal resisting force. So this sum of this force will be equal to F only. This also F only, right? And either sections, the sum of values will be equal to the applied the sum of whole of the value, the resisting force will be equal to the applied force. So I will define the value, define the term called stress. Stress is nothing but stress is nothing but uh, resisting force per unit area, of the cross section. Resisting force per unit area of the cross section. Okay, stress is nothing but is defined as the resisting internal force generated, internal force per unit area of cross section of the body, cross section of the body, right? Not the applied force, resisting force per unit area of cross section of the body, right? So that is known as stress. Then what will be the value of the unit of stress? Unit of stress will be actually stress will be force by area, right? Force by area. Force by area means unit of force is Newton. Newton by meter square, right? So what is Newton per meter square? Newton per meter square is nothing but Pascal, right? Pascal. Pascal is represented by the letter Pa. Pa, Pascal. So other what is usually the value of that stresses will be around maybe different units are used, like what is this? MPa means megapascal. Have you heard? Megapascal. So 1 MPa means how much Pascal? 10 raised to 6 Pascal. What is 1 GPa? 1 gigapascal, 10 raised to 9 Pascal. So various units will be used while doing problems. Okay, so you have to be you have to know all these things. Okay, and now so these are the units of Pascal. So students, hope you have understood what stress means. So different types of stresses. First one, okay, two types of stress can be of two types, mainly two types: normal stress and shear stress. Okay, normal stress and shear stress. This normal stress are of two type: tensile stress, compressive stress. Okay, shear stress only one type. So I will show you the difference, what is normal stress or tensile stress or compressive stress, how they are different from shear stress. Normal stress, first one, normal stress. Suppose I have a body like this. Suppose I am applying a force normal to this particular section. Okay, the direction of force is normal to the cross section area, right? Normal to the cross section area, the shaded, this is the cross section. If the force applied is normal to the cross section, such forces are called normal force. Now normal force can be of two types. Okay, so this is another body. So this is also normal force. because this force is also perpendicular to the cross sectional area. But what is the difference? Here elongation, here that force tries to elongate that body. Here the force try to what, compress. So the the force that's trying to elongate the body is tensile force. The force that is trying to compress the body is compressive force, right? So here also stress will be developed. Here also stress will be developed. The stress developed in the case of tensile force is called tensile stress. Okay. The stress developed in the case of compressive force is called compressive stress. So normally we use the Greek symbol called sigma. Sigma for normal stress. For normal stress. Okay, maybe sigma T is tensile stress, sigma C compressive stress. Okay, so these are the letters, Greek letters, Greek symbols used, because this is universally accepted symbols. Everyone, every text, if a symbol sigma is used, means we are referring to a normal force, maybe either tensile or compressive. If you have a subscript called T, it means tensile stress. If you have a subscript called C, it is compressive stress. So, whatever, sigma is nothing but F by A, where F is normal to the applied area. The direction of F is perpendicular to the area A we are considering. Okay, so that's the idea. Depending upon if it is T, force is tensile. Okay, if we see force is compressive. So that's the difference between tensile force and compressive force. Now I will show the suppose I have a body like this. Okay, so what is shear stress? Shear. Okay, so this is placed on a some floor. Okay, so this is our body. I am applying force on this particular surface. I will show which surface, this surface, that upper surface. Okay, I am applying a force F on that particular surface. What will happen to the body? Since this body is placed on a particular floor, there will automatically there will be a reaction force of F towards opposite direction. So the net effect is like this, F, right? So what will happen to that body? What will happen? There will be a chance of that body getting displaced like this, like this, right? I will show once. This body will may change to a position like this, right? There will be a change in shape. Actually, initially it was at this position. Some displacement of an angle, suppose angle phi, a displacement of angle phi is being taking place due to the application of force F, right? Due to application of force F, right? So this type of here what is how this force is, what is the direction of force with respect to the area of that area that we are considering, suppose the area of that that a particular surface is A. What is the direction of force with respect to that area? Force is parallel 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 to the area. it is being applied parallel to that area. So such force, the stress developed in such cases will be shear stress. Shear stress. So excuse me for my handwriting. It may not look in a neat way, right? Okay. So please excuse me that for. So shear stress. So the what is the Greek symbol? Initially, sigma was used for. Uh, Now this sigma was used for the normal stress. In this case, we will use the Greek symbol called tau. Tau. Greek symbol tau for tau is F by A. Shear stress is symbolized using the Greek symbol called tau. Okay, tau is F shear by area. Okay, so that is the symbol used for shear stress. So what is the direction? How is the internal force generated here? I will show. Internal force here is initially this was the body. Okay, and after the application of force, it gets displaced, it gets deformed in such a manner. Okay, some phi displacement, right? So I am taking a section in this direction parallel to force. Okay, what will happen? The direction of internal force will be in such a manner that it will oppose the effect of applied force. It will. So this is the section applied force F. So in this, the bottom of this section will have so many internal force acting like this. Here, in this manner, here, this is the reaction force. So this will be the internal force in this section. Here also internal forces. Okay. So this is how internal force depicted in the case of so these force by area will give shear force, or these force by area will give shear force. Okay, sorry, shear stress, the internal resisting force per unit area. Since the internal resisting force is equal in value with the applied external force, we are using the same value. Okay, the value will be the same, right? The value of the applied force will be same as that of the internal generated internal force. Okay, so thus you have understood what shear stress is meant by. Now I will move to the concept called strain. Okay, let me take a body with a length of L. Okay, I am applying a tensile force of F. What will happen to the body? The body will get elongated if F remains if you are not changing the value of F. It will get elongated to a length of L plus delta L. Some increase of delta L is, initially it was some L. Initially it was of length L. Now after the application of a force, a tensile force of F is applied, the length increased to L plus delta L, a net increase of delta L. A stretch of an elongation of delta L is observed, right? So I will define strain. Strain is the ratio of increase in or elongation by original length, delta L by L. So the change in length of the particular body per unit initial length. So that is what meant by strain. Okay, that is what meant by strain. So in the case of tensile force, the strain will be here. Strain will be represented using the letter called uh, epsilon. So this is nothing but a tensile strain. Tensile strain. The strain that is happening in the case of tensile force is tensile strain. Okay, let it be T. In the case of compressive force, it is compressive strain. Compressive strain. Right. In the case of shear force. Okay. So in the case of shear force, here how can we get an expression for shear strain? If we are having a change in angle of phi, now in the case of compressive stress and tensile stress, you can use the expression called delta L. But in case of tensile and compressive, in case of shear, you cannot use this particular expression, because here there is no change in length of that body, no change in any dimension. Size remains same, but here shape is being changed. So here I am using the expression called tan phi. Tan phi, the change in that angle is, if the change in that angle is phi, then tan phi will give you the shear strain. Shear strain is nothing but here shear strain using the letter called gamma is nothing but tan phi. Okay, epsilon t or epsilon c, that these are normal strain or tensile strain or compressive strain, will be equal to change in length. Maybe this delta L can be increase in length or decrease in length, because in tensile force you have increase in length. Okay, in the case of tensile force you can have increase in length. In the case of show tensile strain, you will strain or stress, you will have increase in length, right? Compressive, what will happen? Compressive, decrease in length, right? Whatever be it, whether it is either it is increase or decrease, you don't care. The value, if the value is delta L, that value, the magnitude of change divided by original value, that is what strain is meant by in the case of normal stress or tensile or compressive stress. But in the case of shear stress, it is that tangent of that change in angle, tan phi. Okay, tan phi will yield you the value of shear stress. So students, for the time being, I am stopping this session. I think you have understood the concept of internal force, method of sections, the idea of stress and strain, different types of stresses like normal stress and shear stress. And normal stress itself is of two types, tensile and compressive. Similarly, strain, what the idea of strain, the change in dimension of that body, the ratio change in dimension of that body by original dimension. There are different types of strain: tensile strain, compressive strain, and shear strain. Hope you have understood these concepts. If you have got any doubt, feel free to contact me at any time. Thank you.